Energy resources, a scientific and technological problem of the 21st century. As we discussed in the previous lectures, oil and gas are still central to modern life. Our objective is to discuss oil and gas consumption and production. We will distinguish between unconventional and conventional petroleum. Again, in this lecture, petroleum is defined as crude oil and natural gas plant liquids. Here are some of the key references used to develop these lectures. Some of the learning objectives are understanding the differences between conventional and unconventional oil and gas, understanding the notion of permeability, porosity, and viscosity, defining the major oil fields and leading oil-producing countries which provide the bulk of the world oil consumption, defining the leading oil consumer countries and their effects on oil prices, defining ultra-deep water oil reserves and locations of these reserves, defining the countries which have jurisdiction over Arctic oil reserves and the challenges of producing this oil. We would like you to seek the answer to the following questions as you go through this class. Why the reserves of conventional oil are in decline? Where are the major reserves of shale gas? As we have just discussed, oil and gas are still central to modern life. Our next step is to discuss oil and gas consumption and production. We will distinguish between unconventional and conventional oils. Some oil resources are characterized as unconventional because they do not flow like conventional oils. This distinction will become clearer in the latter part of this lecture. We have divided this lecture into 4 parts. We start with a list of basic terms and acronyms generally used in the discussion of oil and gas consumption and production. The second part deals with the decline in conventional oil production and the increasing demand. In the third part, we describe some sources of conventional oil which are yet to be tapped for production. In the fourth part, we will describe unconventional oil as another alternative source which can potentially offset the decline in the conventional oil production. Here are some standard abbreviations used in the description of oil and gas production and consumption. We will start with 1 barrel, which equals 42 gallons, or 159 liters. Note that the acronym of barrel is BBL. Next we have 1 MBBL, which equals 1,000 barrels. 1 MMBBL equals 1 million barrels. The acronym of barrel per day is BPD, or BOE, or BBL/D, or BPD. Let me draw your attention to this acronym because it is probably used the most for evaluating the consumption of oil. Again, BPD is barrels per day. BOE is barrels of oil equivalent. OOIP is original oil in place. OOIP describes the amount of oil after discovery. URR is ultimate recoverable reserves. That is cumulative production plus the estimated remaining reserves. URR describes the oil that we actually end up taking out of the ground. E&P is exploration and production. EIA is Energy Information Administration. This is the division of the U.S. Department of Energy. Upstream is oil and gas exploration and production, or E&P. This is mainly for producing crude oil. Downstream is refining of crude oil and selling and distribution of natural gas and products from crude oil. OPEC is the Organization of Petroleum Exporting Countries. OPEC members countries include Algeria, Angola, Ecuador, Iran, Iraq, Kuwait, Libya, Nigeria, Qatar, Saudi Arabia, UAE, and Venezuela. You are encouraged to refer to this list that we just described as you go through this lecture. Let me recall some basic processes of petroleum. Petroleum reservoirs can be found beneath land or the ocean floor. Their crude oil is extracted with giant drilling machines. Crude oil is usually black or dark brown, but can also be yellowish, reddish, tan, or even greenish. Variations in color indicate the distinct chemical compositions of different supplies of crude oil. It is almost always necessary to refine crude oil in order to make useful products. Oil and natural gas are often found together in the same reservoir. The natural gas produced from oil wells is generally classified as associated dissolved, meaning that the natural gas is associated with or dissolved in crude oil. Natural gas production absent from any association with crude oil is classified as non-associated. Raw natural gas is also processed to remove impurities in various non-methane hydrocarbons and fluids. The results of this process are known as pipeline quality, dry natural gas. The impurities removed generally include water, carbon dioxide, or CO2, and hydrogen sulfide, or H2S. Oil is classified according to three main categories: the geographic location where it was drilled, its sulfur content, and its API gravity. Now we'll talk about oil classification based on API gravity. The American Petroleum Institute, or API, is a trade association for businesses in the oil and natural gas industries. The API has established accepted systems of standards for a variety of oil and gas related products, such as gouges, pumps, and drilling machinery. The API has also established several units of measurement. API gravity is the American Petroleum Institute gravity. It is used to differentiate heavy or light oil. Although API gravity has no units, it is generally referenced in degrees. When API gravity is greater than 31 degrees, oil is characterized as light. When the API gravity is between 22 to 31 degrees, the oil is said to be medium. When the API gravity is between 10 to 22 degrees, the oil is characterized as heavy. When the API gravity is smaller than 10 degrees, the oil is considered to be extra heavy. Light oils are preferred because they have a higher yield of hydrocarbons. Light oils can contain up to 97% hydrocarbons, while heavier oils and bitumens might contain only 50% hydrocarbons and larger quantities of other elements. Now we're moving to oil classification based on sulfur content. Crude oils have few metals or sulfur. Sulfur is considered an impurity in oil. Sulfur in crude oil can corrode metal in the refining process and contribute to air pollution. Oil with more than 0.5% sulfur is called sour, while petroleum with less than 0.5% sulfur is sweet. In other words, sweet oil that has few metals or sulfur, for instance, tends to be lighter, sometimes nearly clear. Sweet oil is usually much more valuable than sour because it does not require as much refining and is less harmful to the environment. The final oil classification is based on geography. Oil is drilled all over the world. However, there are three primary sources of crude oil that set reference points for ranking and pricing other than oil supplies. The final oil classification is based on geography. Oil is drilled all over the world. However, there are three primary sources of crude oil that set reference points for rankings and pricing other oil supplies: Brent crude, West Texas Intermediate, and Dubai and Oman. Brent crude is a mixture that comes from 15 oil fields between Scotland and Norway in the North Sea. These fields supply oil to most of Europe. West Texas Intermediate, or WTI, is a lighter oil that is produced mostly in the U.S. state of Texas. It is sweet and light, also considered very high quality. Dubai crude, also known as Dubai Oman crude, is a light, sour oil that is produced in Dubai, part of UAE and Oman. Dubai and Oman crudes are used as a reference point for pricing Persian Gulf oils. We will now talk about the world petroleum consumption and production. Our focus is on conventional oil and gas. World oil demand in 2011 was 89.11 million barrels per day, and world oil production was about 88.54 million barrels per day. So about 0.6 million barrels per day of spare capacity was needed to keep up with the demand. Oil prices go up at some point. Spare capacity refers to the world oil market's ability to respond to shortfalls in production. The total spare capacity in 2014 was around 0.5 million barrels per day, which provided very little cushion for fluctuations in demand. Let me help you get your mind around the numbers of barrels and spare capacities. If an individual earns $88 per day and spends $89 per day, he or she would need to withdraw $1 per day from savings to keep going. Sooner or later, their savings will run out. He or she will then need to reduce their expenses, seek a higher paying job, or get a second job to keep up. If a society produces 88 million barrels of oil per day and consumes 89 million barrels per day, it would need 1 million barrels per day of spare capacity to keep up with the demand. Sooner or later, the spare capacity will not be there. We will need to reduce consumption, discover new fields, and include renewables in the mix. The world demand in 2014 was 92.4 million barrels per day, and world oil production was about 93.1 million barrels per day. There are about 0.7 million barrels per day of overcapacity. The oil prices go down at some point. Here are the curves of the world production in blue and consumption in red of petroleum. The horizontal axis represents years, and the vertical axis represents the demand and production in million barrels per day. This figure captures the differences between consumption and production for 35 years. Notice how small the margins are between production and consumption. Yet these margins have large effects on the oil price. Yes, these small differences have a huge effect on the oil price, at least in short term. In other words, if for some reason the margins between consumption and production were to drastically change overnight, the oil price could totally collapse or skyrocket. The next question is, what are the chances of such large changes in the difference between production and consumption happening? To answer this question, let us review the leading producers and consumers that can cause such changes. This table shows the leading producers. Besides the United States, and to a lesser extent, Brazil and Canada, we can see that oil production by leading producers has been quite stable, with a small decline by Iran and a small increase by Iraq for geopolitical reasons. The increases in the oil output of Canada and the United States in the last 6 years are shown here. They're primarily due to their production of unconventional oils, which we will describe later. Those of Brazil are due to the exploration and production in ultra-deep waters, which we will also describe later. Note that the oil output of the United States in 2014 increased by 5 million barrels over from its 2008 levels. Without this increase in U.S. oil production, we would not be having an overcapacity in 2014. But we would be looking for more than 4 million barrels per day of spare capacity to keep up with world demand. Such a sparse capacity is beyond the current reserves and/or a world oil output increase in production from existing oil fields. Let's repeat this point because it is very important. Note that the oil output of the United States in 2014 increased by 5 million barrels over from its 2008 levels. Without this increase in U.S. oil production, we would not be having an overcapacity in 2014. But we would be looking for more than 4 million barrels per day of spare capacity to keep up with world demand. Such a sparse capacity is beyond the current reserves and/or a world oil output increase in production from existing oil fields. Note also that the 10 leading producers contribute more than 61 million barrels per day of the 93.1 million barrels of world production in 2014. So there are a lot of small producers that account for less than 1 million barrels per day. You may be surprised to see that countries generally advertised as oil-rich, such as Kuwait, Venezuela, Nigeria, Qatar, Norway, Angola, Algeria, Kazakhstan, did not make the top 10 list. The reputations of these countries as oil-rich is based on the ratio of their oil revenues versus their economies and/or populations, not on their oil output. Let us now turn to the list of leading consumers. Despite a slight decline, the United States is by far the leading oil consumer because of the large size of its economy. China is the second largest consumer of oil, with an average annual increase of 0.5 million barrels per day of consumption. In other words, China alone counts for half of the increase in global demand, which is annually around 1 million barrels per day. The other half of the increase in global demand comes mostly from India, Pakistan, and some Latin American countries. Let's repeat these points. Despite a slight decline, the United States is by far the leading oil consumer because of the large size of its economy. China is the second largest consumer of oil, with an average annual increase of 0.5 million barrels per day of consumption. In other words, China alone counts for half of the increase in global demand, which is annually around 1 million barrels per day. So if the demand in China stalls or declines, oil price can significantly go down. The other half of the increase in global demand comes mostly from India, Pakistan, and some Latin American countries. The increase in oil demand is mostly driven by the growth of the world's population and oil-based industrialization. Therefore, the increase in oil demand is a gradual process, just as is population and economic growth. Oil production, on the other hand, is controlled by many factors. The major ones are the original oil in place, or OOIP, ultimate recoverable reserves, or URR, and advances in E&P, or exploration and production technologies. These factors also tend to gradually affect oil production. Sometimes we can increase production by drilling more wells into oil reservoirs. For reservoirs at the beginning of their production stage, these wells can significantly increase production. However, for old reservoirs, the increase in production is marginal, less than 5%. Moreover, on land it takes weeks to drill new wells, and in marine it takes several months to drill new wells. Advances in exploration and production technologies and the discovery of new fields have to allow oil production to track the oil demand and sometimes produce slightly more oil than is needed. However, most projections, like the one shown in this figure, suggest that a wider gap may open between oil consumption and production. Our next discussion focuses on factors which can justify such a gap and describe some emerging solutions. Supergiant oil fields have 5 billion or more barrels of recoverable oil. To get our minds around this huge number, 1 billion barrels represent only about 11 days' worth of world oil supplies. So at the current consumption rate, the Ghawar Oilfield in Saudi Arabia, which is the largest oil field ever discovered, with 100 billion barrels of reserves, will be depleted in 3 years. The next category below the supergiant oil fields are the giant fields. These are fields with 500 million or more barrels of recoverable oil, but less than 5 billion barrels. These tables provide the top 20 major supergiant oil fields, along with the years of their discoveries and their ultimate recoverable reserves, or URRs. Notice that most top supergiant oil fields are located in the Middle East, 16 of 20 of them. Only one supergiant in Europe, Samotlor, Russia, 2 in North America, Prudhoe Bay, Alaska, and Cantarell in Mexico, and 1 in South America, Bolivar Coastal, Venezuela. There are none in Africa, none in Asia, and none in Australia. The theoretical distribution of large accumulations of oil around the world is not completely understood yet. Let's talk more about the Ghawar Oilfield. The Middle East has 80% of the world's remaining conventional oil. Ghawar Field in Saudi Arabia had 100 billion barrels of reserves. Only one field of this size has been discovered. 5 supergiant oil fields and 3 giant oil fields make up 98% of Saudi output. These oil fields are between 40 and 60 years old. Ghawar was discovered in 1961 and reached its peak production in 1980 with about 6 million barrels per day. Today, Ghawar's production is below 4 million barrels per day, despite the large number of wells drilled, about 3,400, and the 7 million barrels of water pumped into the reservoir daily to improve recovery. Note that our definitions of supergiant and giant oil fields are based on recoverable reserves and not on estimated reserves. Other examples of supergiant oil fields include China's Daqing, found in 1961, Russia's Samotlor, found in 1963, Alaska's Prudhoe Bay, found in 1967, Cantarell in Mexico's Bay of Campeche, found in 1975. Let's talk more about the supergiant Prudhoe Bay. It was discovered in 1967 with 13 billion barrels of recoverable reserves. From 1979 to 1989, Prudhoe Bay's production stayed at 1.5 million barrels per day. From 1989, when Prudhoe Bay peaked, its production experienced a steady decline, despite aggressive drilling to create more development wells and reinjection of all the dissolved gas produced with its oil. At the end of 2004, oil output from the original Prudhoe Bay field, excluding several satellite fields, was 300,000 barrels per day. The decline of production of the supergiant oil fields is a worldwide phenomenon. Despite the recent discoveries in the Gulf of Mexico, the Prudhoe Bay oil field remains the largest oil field discovered in North America, excluding Mexico. Let's talk about the supergiant Daqing in China. Discovered in 1961, the Daqing field has sustained oil production above 1 million barrels a day for over 35 years. Since the field is onshore and the wells are inexpensive to drill, this steady production was maintained by constantly drilling more and more infill development wells at increasingly tighter intervals. A decline in Daqing's production was revealed in 2008, but no details were given. Now let's talk about supergiant Samotlor in Russia. It was discovered in 1963. Samotlor's oil output was 1.5 million barrels per day until political pressure took advantage of the rising price in the early 1980s, led to aggressive water injection to increase production. In 1983, its production briefly hit 3.5 million barrels per day. In 1999, Samotlor's output fell to 300,000 barrels per day. Let's talk about Cantarell supergiant oil field in Mexico. The second largest producing field in the world is the Cantarell complex in Mexico. It lies 85 kilometers from Ciudad del Carmen. The field was discovered in 1976 and began production in 1979. Cantarell was the last oil field found anywhere whose daily production exceeded 2 million barrels per day as late as 2004. In 2009, Cantarell's oil output fell to 700,000 barrels per day. We can see from these examples that the world conventional oil supplies are dwindling. All the major conventional oil fields were discovered long ago, and many have exceeded peak production and are in decline. Spare capacity is about 0.5 million barrels per day on average. The discovery of giant oil fields, that is greater than 0.5 billion barrels, has decreased to near zero. Small discoveries are occurring, but not at a sufficient rate to offset the production decline of giant fields. Global demand per day is expected to increase by at least 1 million barrels each year on a 10-year average. M. King Hubbard, a geophysicist with Shell and the USGS, introduced the peak oil concept in 1956 and forecast that U.S. crude oil production would peak in 1970. He was right, if you exclude unconventional oils, as you can see in this figure. The basic idea is that fossil fuel, coal, oil, and natural gas production in a given region over time will follow a roughly bell-shaped curve. This idea is known in statistics as the central limit theorem. Obviously, unconventional oils are bringing the oil and gas production back up again in the U.S. Here are the peak conventional oils. Notice that most of the major producing countries passed their peaks in the 1970s. Actually, all the major producing countries passed their peaks more than a decade ago. Through billions of years of biogenic and thermogenic processes, the Earth has naturally produced large accumulations of oil, such as Ghawar, Samotlor, Prudhoe Bay, and Cantarell. Through exploration, all the supergiant and even giant fields were discovered in the 1940s, 1950s, 1960s, and 1970s. No new giant fields will be found for a while, irrespective of technological advances in oil exploration. We will have to wait a couple of million years to discover new giant fields. In summary, why are oil supplies peaking? We are not finding new oil fields fast enough. We are not improving the recovery factor in existing fields fast enough. Too many fields are old and declining. Society's demand for oil has not stopped increasing. In only 100 years, mankind used more than half of all the oil on the planet. Oil that took billions of years to produce, and that is the result of climatic conditions that existed at only one time in the Earth's 4 billion year history. Oil is a non-renewable resource. We have now concluded our discussion of conventional oil and gas production and consumption. When we return, we will describe the new frontiers of conventional oil and unconventional oil and gas resources.